every single day there's another problem to do. This is 4544 sum number 2. For sum number 2. Okay. So, if you have any familiarity with any class of Leetcode problems, data structures, algorithms, competitive programming, technical interview contexts, the two-sum class of problems are perhaps the most popular and the most infamous set of problems, right? You see them in interviews all the time. They're super common, so they're definitely a class of problems that you should solve before you go into an interview, because even if there are thousands of problems, for whatever reason, this problem or some problem that is similar to this problem within the same domain, classification, whatever, is extremely common, okay? So with that said, let's go ahead and get into this. I don't know. Okay, so we're given 4 integer arrays, nums1, nums2, nums3, num4, all of the same length n, okay? So there's 4 arrays, they all have the same length. Return the number of tuples, I, j, k, l, such that, all right? So we're returning tuples that are within the range of the array, right? So it's within 0 and n, between 0 and n. And it's the case where nums1 of I plus nums2 of j plus nums3 of k plus nums4 of l equals 0. So what does that mean? So that means that we select an element from nums1, we select another element from nums2, we select a third element from nums3, and we select the last 4th element from nums4. We add them all together, and if we get 0, that is a solution to this problem, right? So we have to select one element from each array. We add them up. If it equals 0, then it's a solution to this problem. Okay, it's another way of stating, this in a much less formal codification. So we want to return the number of pairs such that exists, right? So when we're looking at nums1, nums2, nums3, nums4 equaling this, well, if we take, what can we take? We can take 1 from here. Or no, we could take 2 from here, right? And then we could take a -1 from here. And then we could take a -1 from here. And then finally take a 0 here. And what does that give us? It gives us 0. We could also take a 1 here. We could take a -2 here. We could take a -1 here. And we could take a 2 here. And if you add those up, you get 0. And that's what we see here, right? So it's talking about the tuples in terms of their indices, right? But I'm talking about them in terms of the actual values, right? The actual values are what matter, right? So you have 1, -2, -1, +2, 1, -2, -1, +2, and 2, -1, -1, 0, 2, -1, -1, 0. So, a different way of stating the same thing, okay? So with that said, there are 2 solutions to this problem. So then it returns 2. So it's pretty intuitive, makes sense. The description is very short. If you've done similar problems, this is something that you're definitely familiar with. So then begs the question, what is the solution? Well, this is definitely one of those problems where it might be beneficial to first state or write or discuss the brute force solution and then see if you can tweak that to find the optimal solution. Okay, now the brute force solution is pretty straightforward, right? What we'll do is we'll say res is the number of solutions that we have, and then we'll just look at each pair of numbers, right? We'll look at all num1s, all the numbers in num1s, we'll look at all the numbers in nums2, we'll look at all the numbers in nums3, we'll turn off caps lock, in nums3, and then we'll look at all the numbers in nums4. And then what we say is, well, if the first number, so if a number from the first nums plus a number from the second nums plus a number from the third nums equals 0, then we add to our solution. Otherwise, we don't, and at the end, we just return res because that would be the answer to the problem, right? Now, this is all fine and dandy. It shows that, you can approach a problem. You're not going to be stuck all day and being unable to find any solution, right? This is a solution. What the issue is given the constraints, this is going to take far too long and you're going to get a time limit exceeded error. Now, why is that the case? Well, all the size of the arrays are the same. They're all size n, right? And n is less than or equal to 200, right? So n is less than or equal to 200. So we'll just say that in the worst case, n is 2 times 10 squared, okay? So in the worst case, what does that mean? Well, what is the runtime of this equation? Well, this is going to take n time For n num1s, we have to look at n nums2. For n num1s and n num2s, we have to look at n num3s. For n num1s times n nums2 times n nums3 times n nums4, we have to do this constant check to find if it's a pair. So that's n times n times n times n, or n to the fourth possible operation. So in the worst case, this is going to take 2 to the fourth times n to the squared to the fourth, which is, you know, this is 16 times 10 to the eighth. So that far exceeds what is acceptable using a Leetcode standard, right? So you can always look at the constraints that not always, you should always look at it, but sometimes it'll indicate whether or not your solution is sufficient. And when we look at this and we say, okay, if we do this brute force approach, we'll get 16 times 10 to the 8 operation flops, whatever. That's our worst runtime complexity. And that far exceeds, not far exceeds, but that exceeds what is kind of acceptable given Leetcode. You know, usually something around, you know, approximately 10 to the 6 is the limit. 60 to the 6. Approximately 10 to the 6 is the limit, right? That's the most number of operations, right? That's the most operations that we can execute prior to reaching a time limit exceeded. So what does that mean? Well, since this number is greater than 10 to the 6, then it's probably going to lead to a time limit exceeded. So then this solution, therefore, is not an answer. So we have to find some modification or some alternative to solve this problem in order to be within the constraints and just, you know, pass without getting a time limit exceeded error from the autograder. Okay. So what can we do to make this better? Well, you know, like I said, this is a problem from this classification of two-sum problems, right, which are pretty common. So maybe we should start with some kind of alternator, some sort of two-sum problem, and see if we can look at the solution to that or find a solution for that and then use that to then solve this, right? Why don't we kind of, you know, break down this problem into more fundamental components and solve an easier version of this problem and see if the easier version solution is applicable to this more complicated variance. Okay. So with that said, what if we were just looking at nums1 and nums2? Okay. That is, we were looking for a solution where n1 plus n2 equals 0. Well, in order to do that, you know, it'd be pretty similar, the brute force solution, right? We would just look at all n1s, n2, and we'd say if n1 plus n2 equals 0, we add that to res. Now, another way of stating this is, well, n1 plus n2 equals 0. That's the same thing as saying, well, we can subtract n1 from both sides, right? This is an algebra equation, so we can subtract n1 from both sides. So I can restate this by saying, well, this is actually, okay, n1 minus n1, that goes away. And then 0 minus n1 is negative n1. So that's the same thing you can state here, right? You can say if n2 equals negative n1, then we add 1 to res, right? If we're looking for just this case where n1 plus n2 equals 0, which makes sense, right? For n1 plus n2 equals 0, then one of them has to be the opposite of the other, right? So if the number we're looking at is the opposite of the other number, then we add 1 to res, okay? But I guess one way you can look at this and say, well, in order for it to equal 0, you know, what we're trying to do here is we're trying to say, well, in order to get 0 with n2, we need the opposite, you know, negative n1 in nums of 1, right? We need the opposite of n2 in n1, right? N1 has to be the opposite of n2, right? So I need in order to get a 0 with n2, I need the opposite of n2, right? I need the opposite of n2 in nums 1, right? So I don't need to look at all of n1s. I just need to say, okay, I'm n2. In order for me to get to 0, I need the opposite of me. I don't need to look at all the n1s. I just need to know if it exists. So I can say, well, if the opposite of n1 is in if the opposite of n2 is in nums of 1, then I add it to res, right? What I'm basically saying is I'm negative n2. So I'm m2. So in order to get to 0, I need negative n2. So then all I'm doing is it's similar. It's the same thing, right? I'm just saying, okay, is the opposite of me in nums1, right? That's the same thing as saying, do I equal the opposite thing? So I'm just saying, well, is the opposite of thing of me in nums1? Is the opposite of me in nums1? Well, you might look at this and say, well, okay, then that means we can do this instead. We can just solve the problem like this. But you'd argue, well, this isn't really a benefit, right? You're not cutting down the runtime because you have to look at all n2 nums, and then for each n2 num, you have to look through all of nums1 to see if the opposite of n2 is in there. But this can be easily optimized by taking nums1 and converting it into a set, right? So now what I'm saying is I look at all n2 and I say, is the opposite of me in nums1? And instead of taking linear time, it'll now take constant time because I'm converting it to a set where I can do constant lookups, right? So this is a situation where I'm going to leverage data structures that offer me improved runtime complexity in order to optimize the runtime totally of my solution, okay? So when we're looking at this, what we basically did is, well, we thought of it in terms of n1 and n2, and then we modified this equation to say, okay, what does that mean in comparison to the two numbers? And then I thought of it, well, that means I don't really need to look at all of the n1s and compare it to each of the n2s. For each n2, I just need to see if its counterpart, right? If its counterpart exists in nums1. Well, checking if it existed in nums1 takes linear time. So can I use a data structure, for example, in this situation, a set, to modify nums1 into something where I can make constant time checks? So now this goes from n squared to n. So that's kind of a solution to this two-sum approach where you have two arrays and you're trying to see if they sum to 0. Can we then use this to get our solution down considerably from n to the fourth to something that will pass the autograder? Well, I guess what we could do, right, just thinking about it here, is, well, you know, we're trying to figure out if n1 plus n2 equals n3 plus n4, right? Now, that's the same thing as saying n3 plus n4 equals, I'm not going to do all the math again, n1 plus n2, right? So that means here, in order to get 0, right? In order to get 0, we need the opposite of n3 and n4, right? We need the opposite of n3 and n4 to get 0, right? That's what I'm basically saying here. So we need the opposite of n3 and n4 to get 0. And then doing the same thing, right? Before, when it was here, we said, well, if the opposite is in nums1, right? But we need something that's not just nums1 and nums2. We need something that's the combination of nums1 and num2, right? So if we say, okay, is the opposite of n3 and n4 in some new nums1, 2 array, okay? And we'll make that a set or a hash table or something to then update this solution. So now we have this created, but we need to know all possible nums1, nums2 pairs that we can get that we can check if the opposite exists. So instead here we can create this nums1, nums2 array, and we'll actually make it a set. All right. Now this isn't the complete solution that I'm doing here. So if you're watching this and thinking, hey, you're missing a key component, know that I understand that, but after I solve it this way, we'll add in that extra little layer of complexity, which is a little dissimilar from this approach over here, which I'm now going to erase. We'll say, okay, we'll look at all combinations, right? Because we'll look at all nums1, nums2 that could possibly exist, and we'll add that to this set here. And if the opposite exists, we'll add it here. So now we've taken this from n to the 4 to n squared, right? I use this idea from, the 2 case. So we look at all n3, n4 pairs, and we'll see if its opposite exists in this nums1, 2. Well, what's nums1, 2? Nums1, 2 would be all the possible combinations that you could get from adding the first two numbers together. So now we kind of cut this runtime, not in half, but like logarithmically, right? Something like that. Right, so we took it from n4 to n squared. All right. Okay, so this is 0. That's not good. Oh, not equals if it's in there. Right? If it's in the set, meaning that the solution exists. So there's been a fail. Because there are kind of things we have to think about. Okay? I didn't see what the wrong... I was hoping maybe something a little bit easy to understand. Okay, well, we're getting an under count here. All right, we're getting 3 when the answer should actually be 6. And my suspicion is, given that there's repeats, right, is that we're not looking for like unique pairs of elements that count up to 0. We're looking for any indice, right? So if this -1 works with something, the other one will as well, right? Like since we have 4 here, okay, size 2, I have -1, 1, 1, -1, right? That equals 0, right? -1, 1, 1, -1 equals 0. But also, también, as well, I'm learning Spanish. Also, as well, this -1 works the same. -1, 1, 1, -1. So there's 2 solutions using -1 here, using this -1, using these 3 ones, right? You can use either this first -1 or the second -1. But using this solution, we're not counting multiplicity, right? We're not counting the number of times that something occurs. We're just counting if it occurs. So we need to somehow add that into our solution. That way we get the right count for res, right? Because res right now is only going to account for that once, even though we have 2 -1s here. So what we'll do instead is we'll create nums1, 2 and do a default dict where the standard value is 0. And then for each nums1, 2 that nums1, nums2 pair that we see, we'll just say nums1, nums2 plus equal 1. Right? And then it even makes this easier because we could just take nums1, 2 negative nums3 plus num4. Right? Because now it'll tell you the number of times that count exists, right? So when we have when we have n3 plus n4, the negative of that is some value like 5, right? So maybe we need a 5 in order to make n3 plus n4 equals 0, right? So the counterpart to n3 and n4 is 5, all right? So how many different ways can we get 5? That's basically what this is doing now, right? You get 5 with 1 and 4, or 2 and 3, or 3 and 2, or whatever, right? How many ways do we get 5 in this solution? And now this accounts for that multiplicity issue, right? And then also, since we're using a default dict, if the number that we're looking for, say we're looking for 5, but 5 never exists in nums1 and nums2, well, the default dict will default to the value 0. So we'll just add 0 to the solution. So it's the same thing as saying, if it's not in there, add nothing. Adding nothing is equivalent to adding 0. Okay. So let's go ahead and that. Okay. Cool. So what's the run and space time of this solution? Okay, so let's say n is the length of nums1, which is also the length of nums2, etc. Our original solution was n to the 4. So let's do time first. So we have to look at all nums1, and for each nums1, we have to look at all nums2. So that's n squared time. Okay, so big O of n squared, plus another n squared to look at all nums3, all nums4. They have the same length, so it's going to be the same time. Right, so it's 2n squared, which is just big O of n squared. And then for space, well, the only thing we really create is this constant. Who cares? We create this default dict. We have to put at most n squared values in this default dict, right? Because it's possible that, maybe you have like, I don't know, prime numbers, prime numbers in nums1, prime numbers in num2, whatever. You can think there's a way that you can have it situated that each multiplication results in a unique number, right? So each multiplication results in a unique number, meaning that, there's a bunch of ways. I'm thinking about all the ways you can do it. Each multiplication results in a unique number, so then you need a unique instance in each default dict, right? So you need a unique key in the default dict for each result, and there could be at most n squared results. So that's also n squared time. Okay. All right, guys, and then maybe there's some log runtime of populating res, but that's going to get overshadowed by this n squared. That's the beauty of space-time complexity analysis. All right, guys, that's it for today. Boom, boom, ba-bang, ba-bang.